Okay, let's start. Good morning. So this week we're going to study this notion of orthogonality. So really this idea of geometry really starts to come into play. And then once we're done with the basics of this, we're going to combine the stuff that we learned last week, spectral theory, eigenvalues, eigenvectors and everything, and what we're learning this week. And that's going to lead to spectral theorem and the singular value decomposition. These are sort of probably the core of this introductory class in linear algebra. Before I go into this, I wanted to mention one thing. I think it was an error that I made. So the constant term of the characteristic polynomial, right? So the characteristic polynomial of an n by n matrix. So if A is n by n, its characteristic polynomial, char sub A with unknown lambda or variable lambda is nothing but the determinant of lambda I minus A. So here I is the n by n identity matrix. I scale it by lambda. So now I have lambda on the diagonals and then I subtract A. This again is an n by n matrix and I can look at the determinant. Since lambda is variable, now it's a polynomial, it turns out. So the constant term of this polynomial, right, so degree 0 term, is char sub A of 0. Right? When I plug in lambda equals 0, I get this, which is really this. And I think I was somewhat confusing about this, so what this really is. So when you think about this, from here to there, I have a scalar, which is -1, and I'm scaling every single row of A. For each row, I should get a factor of -1. Since A has n rows, ultimately, this should equal to -1 to the n times determinant. Okay? That is to say, the constant term of the characteristic polynomial of the matrix is determinant if your dimension n is even, for instance, if you're looking at 2 by 2 matrices, or it is minus determinant if you're looking at, for instance, 3 by 3 matrices. I should also mention that in some other books, instead of defining the characteristic polynomial this way, they define it the other way around. They say the characteristic polynomial really is A minus lambda I. So everything sort of changes up to a sign. But these are pretty much both common conventions. The benefit of defining it this way is that you know that the leading term is always going to be lambda to the n instead of minus lambda to the n. And as far as I know, or as far as I have experienced, it's much easier to compute things if you have lambda to the n, if you start with lambda to the n instead of minus lambda to the n. This is just like a minor point, but I wanted to clarify this. Now, orthogonality and inner product spaces. This is all about this dot product of vectors. So recall that the dot product, so the inner product or dot product of vectors was this, right? So if I have V and W in Rn, n-dimensional vectors, well, V dot W is nothing but, in terms of matrices, V transpose times W. Okay? So now if I think of these vectors as column matrices, these are n by n, is n by 1. So V transpose is going to be 1 by n. So ultimately, this is just going to be a 1 by 1 matrix. Whatever that number is inside that matrix is the dot product, is the outcome of the dot product. So maybe I should write it explicitly. So if V has entries V1 to Vn, and W has entries W1 to Wn, then their dot product is going to be this. So let's compute it over there. Now, this is V transpose, okay? This is not the tuple. You see, I'm not writing the parentheses here. So this is not quite the same, exactly the same thing as this. This is just a matrix. This is a tuple. And underneath this identification of this with this, there's a choice of basis. But of course, at this stage, we're not going to discuss that too much. So when I put this like this, now this matrix multiplication is well defined. So this just gives me this. And using this summation notation, you can write it like so as well. Sum all terms vi, wi, where the index I runs from 1 to n. Okay? Now, instead of using this dot notation, I'm going to use a slightly different notation. I'm going to write instead of this, this. This is going to be my notation for this. Okay. There are other notations. For instance, physicists use this bra-ket notation is what it's called. This is like the physicist's notation. They're all the same thing. But I'm going to stick to this. Because especially in the context of function spaces, this can get confusing, whereas this is rather more straightforward. So this is the inner product of two vectors. Of V of the vectors V and W. Let me define a couple more things. If I were to take the inner product of a vector with itself and then take the square root of that result, that's called the norm or length. So you just write it like this. It's almost like an absolute value. Some people use 2 bars. Instead of writing it like this, they write it like this. I think it's clear from the context. So this is defined as the square root of V inner product with itself. And when I write this out, this really gives me this. So the square root of V1 squared plus V2 squared plus Vn squared. And then you take the square root of everything. Another thing is distance between two vectors. Let's just write it like this. In the book, they just write dist. I'm just going to write instead just d of V, comma W. This is nothing but the norm of their difference, which when you write it out, turns out to be this. Vi minus Wi squared, I from 1 to n, then you take the square root. Okay, these are the 3 notions. But you see, it all starts from the inner product. Inner product gives you a notion of length. The length gives you a notion of distance. Now, it is not necessarily true that all distances come from a length and all lengths come from an inner product, but in this case, they do. Okay. So here's a couple of examples of computations. For instance, let's look at these matrices or vectors. In 3 dimensions, we have. So let's look at this. 2 minus 5 minus 1 is the first vector. And then the second vector, 3, 2, minus 3. Okay? So now if I were to take the inner product of these, so you multiply this and this, that gives you a number, and then this by this, and then this by this. And then you add them up, okay? So 2 times 3 plus minus 5 times 2 plus minus 1 times minus 3. That is to say this is 6 minus 10 plus 3. This is minus 1. In a second, we're going to discuss how to interpret this, what this number really tells us. But for now, let's just compute things. So this gives me this. If I were to look at inner product of u with itself, now all I'm going to do is I'm going to square all of these entries, right? And then I'm going to add them up. So that gives me 2 squared plus minus 5 squared plus minus 1 squared. This is 4 plus 25 plus 1. Oh, 30. Yes, 30. And so if I were to consider the norm of u, or the length of u, I need to take the square root of this. In this case, I mean, this is just root 30, of course. Let's look at the norm, sorry, the inner product of v with itself. Or maybe I should do this. Let me look at the inner product of u with twice v. Okay? So this is 2 minus 5 minus 1. Inner product with 6, 4 minus 6. And then multiply these. This is 12 minus 20 plus 6, which is minus 2. And of course, this is twice this, because, so, you know, you can pull out the numbers essentially. Okay. What is the norm of twice v? Any guesses?
2 times the norm of v?
Yeah, right. It should be that way, but let's go through the motions. So this is 2 times v, inner product, and then square root. So instead of taking the square root here, you can take the square here to get rid of this gnarly expression over here. So it's much easier to compute the square of the norm and then take the square root of the end result. So let's compute this. This is 6, 4 minus 3, and then 6, 4 minus 3 again. And then this is going to give you 36 plus 16 plus 9. So now what is this? 45, 55, 61, I think. So that means that twice the norm of, so norm of twice v is root 61. Let's just verify that the norm of v is half this. This is this, this. So this is 9 plus 4 plus 9. This gives me 18, 22. Maybe I made a mistake somewhere. That's because I didn't multiply this. Minus 6. Minus 6, so that's 36. So now 72, 88. Okay. So 88 is 8 times 11. 8 is 4 times 2, so this is 2 root 22 squared, which means that this is 2 root 22. And there you go. The norm of v squared is 22, which means that the norm of v is root 22. And so we get the thing. Okay. There's a bunch of rules as usual, but I'm just going to leave it to you to sort of discover them as you're computing things. Any questions about these so far? Okay, so now let's start to connect this to geometry a little bit. Let's start with the norm. Another name for this is the magnitude. Let me write that down as well. The relation between a norm, a vector and its norm is approximately the relation between a vector and velocity and speed. So velocity is, as a physical notion, tells you in which direction you should be going. Speed doesn't tell you which direction you should be going. It's just a number. So let's do it in 2 dimensions, for instance. If I were to look at v, which is 2, 5, for instance, this is a vector in 2 dimensions. 1, 2, 1, 2, 3, 4, 5. So it's somewhere here. Its norm is 4 plus 25 in square root, which is root 29, which is exactly from standard basic geometry the length of this hypotenuse here, right? Because this has length 2, this has length 5, and so the length of this is the square root of the square of this plus the square of this. So the norm of a vector is the same thing as its distance, essentially, of the endpoint from the origin. Okay, this is the case, of course, in general as well. And if I were to, for instance, take another vector, I can look at the distance between these 2 vectors. And that's going to be the distance that you're comfortable, that you're familiar with from basic geometry. So here's another example. Let me take the same vector over there to 5, and then let's say w is 1 minus 3. So let's draw this. 1, 2, 3. Okay, so this is 2, this is 5. So this right here is v, and this is 1, this is minus 3, which means that this right here is w. Now, if I were to look at the distance between v and w, according to this definition, it is nothing but the norm of their difference. Now, what is this vector? This is 1, 8 in norm. So that norm is 1 plus 64 is 65, and then take the square root, root 65. This is 5 times 13, so we cannot go further, at least without a calculator necessarily. So it should be the case, and then this distance from, so the length of the line segment that connects V to W should have length root 65. Yeah, so I want to figure out the length of this line, and I want to see, so one way to compute this is to figure out or come up with a certain right-angled triangle. And so you can look at this triangle over here, okay? And then you can do the Pythagorean theorem to come up with this length. So this has length 1, and then this has length 1, 2, 3, 4, 5, 6, 7, 8. Okay, gives you the same thing. Okay? And of course, the same thing holds in general if you had n-dimensional vectors. Now we can talk about their norms. That is to say, these are, so the norm of a vector is how far that vector is, or its endpoint is, from the origin. And you can look at the distance between two vectors. And I hope at this stage you can really imagine how this could be useful, because we have function spaces as vector spaces. If you can come up with some sort of an inner product on this function space, and people do that, then you can really start talking about distances between functions. We're not going to get there for now, maybe ever in this class, but it's a thing. It's a thing that people do. Any questions so far about these calculations?
When you talk about distance with function spaces, is it to measure accuracy relative to something else? I mean, I'm sure that's one.
Yeah. That's one way of thinking about it. So you want to be able to say, oh, I have this function, and you want to say something like, oh, I want to approximate it. But in order to approximate something, you need something like a metric, right? So there are a couple of ways of doing this. And this really this is really why in infinite dimensions, linear algebra is not quite the complete set of tools. You really need to start talking about the calculus of things.
Another question.
Yeah.
Like, I thought it was pretty interesting. You know, you introduced like the dot product, but then we ended up talking about like basically like tangent.
Yes.
Right. And I was wondering if there's ever a situation in which, rather than talking about like the linear algebra between like, you know, a set of vectors, if you use trigonometry to sort of like help you, where the linear algebra might be really weird, or maybe where like the linear algebra is derived from trig or somewhere else. You know what I mean?
Yeah, I mean underneath.
I guess it's kind of like the same. It's like coming from the same thing.
Well, let me say it this way. So this dot product has to do with the angle, really, and we're gonna see that in a second. But they are like intricately connected. Let's put it this way. Yeah. So this notion of norm or magnitude or length, as well as the notion of distance, match with our understanding as to how they should operate. Let's really now think about the inner product. The idea is that the inner products are related to angles. Okay, and so here's the idea. Let's do it like this. Okay. I'm taking two vectors, u and v, in Rn, okay? But certainly, if I'm just looking at two vectors, I can look at this two-dimensional slice spanned by them in this n-dimensional space. So this is like a two-dimensional section of my n-dimensional space. So all that matters is that I get to see u, v, and the origin as part of the same two-dimensional space. So I would like to relate the inner product of u and v to the angle between them. So let's call this angle theta. Okay, so the theta is the angle from u to v. This perfectly makes sense. Maybe I should record it over here too. Rn. Now, u, on the one hand, is this endpoint, but I can really think of this as the arrow from the origin to this endpoint as well. And based on what we discussed, the length of this line segment is the norm of u. Okay? And then the length of this is the norm of v. Can I say anything? Can I say something about the length of this relative to u and v? Like in terms of u and v, how would I describe the length of this?
Norm of v minus u.
Right? Because u is taking you from here to there, and then v minus u is yet another vector. And if you were to add it to this, you would end up at v. So this is v minus u in norm. Okay? Probably I should have drawn this larger, but let me just put this v over here. So now I want to relate the inner product of u and v to theta. Let's do this. If I were to draw this line, now this length here would be norm of v times cosine of theta. Okay. And maybe I should use a different color. So this would be norm of v times cosine theta. And the length of this yellow line is norm of v times sine of theta. And of course, this right here is, it has length norm of u minus whatever this is. Okay? But then I can apply the Pythagorean theorem to this to relate this to this and that. So Pythagorean theorem, let me etch it with blue here. This 90-degree triangle gives that u minus v norm squared or v minus u norm squared, equals this squared plus this squared. Okay, let's open these up. So the left-hand side is v minus u squared, norm squared. This is nothing but v minus u inner product with itself. And then you can open this up. It turns out that this is equal to this. So the property I'm using is that for any fixed first vector, this is going to be a linear transformation and vice versa. So maybe I should do this step by step. So I'm fixing the first vector, and then I can open this up. And then minus v minus u, comma, u. And then fixing this, I can open this up as well, and likewise this. That gives me this. This is the first part, and then I have here similar things, minus v against u, and then plus u against u. Okay, now this is the same thing as this. The order doesn't matter here, because you're just multiplying the entries and then adding them up. And this is the norm squared of v, and this is the norm squared of u. Okay, so this is the left-hand side. And you see, from here we have this inner product of u and v. This I obtained by opening up this left-hand side. Now I need to do the same thing to the right-hand side. So now the right-hand side over there is v norm squared times sine squared of theta plus u norm squared minus 2 u norm v norm cosine theta, and then plus v norm squared cosine squared of theta. Now consolidating this with this, we know that sine squared plus cosine squared is 1, so this just gives me v norm squared. So this has to equal to this. These go away, these go away. So this has to equal to this. Okay? So when you're taking the dot product or inner product, you're really looking, so whatever number you're computing is up to some lengths. You're really looking at the angle. And if you want, you can say theta equals this divided by these two, and then you take the arc cosine if you want. So the angle between u and v is the arc cosine of u against v divided by u, v in norm. You can write it this way as well. Okay. Now, based on this, you say that two vectors are perpendicular or orthogonal to each other if this angle is 90, right? And that exactly happens if their inner product is 0. So, definition. Two vectors are orthogonal or perpendicular okay, if their inner product gives you the number 0. Yes?
So does that mean every vector is orthogonal with the 0 vector?
Yes. Yeah, this is like the legalese that just creeps up. You define something, and then there are like edge cases, and yeah, you have to say that the 0 vector is orthogonal to everything. Let's write it. Zero vector is orthogonal to any other vector. To any other vector. And then the notation for this orthogonality is this. U perp is the name, V. That's what you write. Okay? Any questions so far? Yes.
But how do you interpret two vectors being orthogonal beyond those dimensions? Like, what do we associate that word to mean?
Well, that's the thing. So if I have two vectors, I look at the span of them. That span is at most two-dimensional. Either they are proportional, in which case it's going to be one-dimensional, right, the span, in which case it doesn't really give you too much information what their inner product is. But assuming that they are linearly independent, their span is going to be a two-dimensional subspace. Now, in that subspace, I can definitely draw things. And it literally is the same thing. Yeah. So this slice here is a two-dimensional slice in R2, in Rn. Maybe I should write it. So this is a this is the 2D subspace of Rn spanned by U and V. And inside that two-dimensional space, that's literally what that means. Perpendicularity, or the angle, makes perfect sense. Okay. Any questions about this? Now, we had discussed this notion of an orthogonal matrix. It should be related, and it is indeed. A matrix of the orthogonal means that its columns are orthogonal to each other. And it also turns out that the length of each column, considered as a vector, is 1. So let me write it here. Let Q be orthogonal. That is to say, it's an orthogonal matrix. By definition, this means that Q transpose Q equals identity. Okay? So let's write this out. So this is Q, and then I need to put Q transpose next to it. So this is Q transpose. I guess I'm going for this other equation, which is the same, of course. And I want this product to give me the identity matrix of dimension n, or n by n. Okay? Now writing out this product, let me abbreviate. So I guess this is Q. So this is row 1, row 2, row n, and this is also row 1 of Q, row 2 of Q, because the entries are always the same, you see. And this is the row n of Q. Right there. So first row, second row, and so on. And then the nth row, like this. And then the first row this way now, second row this way, and then the nth row this way, gives me this. Right? That's the identity matrix. Now 1 equals R1 times R1, inner product. So R1 norm squared equals 1. That means that R1 has norm 1. And if I were to look at, for instance, this entry, that would correspond to taking the second row here and the second column here. So that I have instead, I can write it like this. The length of any row or any column, it doesn't really matter in this case, is 1. And further, if I were to take different rows, for instance, row 1 against row 2, that would correspond to this, and it would be 0. And based on our definition, that would mean that the rows are orthogonal. Okay, so the rows of an orthogonal matrix each have length or norm 1, and they are orthogonal to each other. Here we started with this equation. Q transpose equals identity. But for an orthogonal matrix, the other way around is also true, and I'm going to leave that to you. if you were to start with Q transpose Q equals identity, you would realize by the same argument that each column has length 1 and distinct different columns are orthogonal. So exercise. Each column of Q, orthogonal matrix, has length 1, and distinct columns are perpendicular, orthogonal. And okay? So you got to start with this equation. Write it out explicitly and realize. Okay? Questions so far? Let me give you one more definition. We have some time. Given a subspace, I can look at its so-called orthogonal complement, which also turns out to be a subspace. Here's a definition. Let S be a subspace. Its orthogonal complement and this is denoted by S to the perp, S perp, is, by definition, is defined as this. It's a collection of all those vectors that are perpendicular, that are orthogonal to any vector in S. So V in Rn such that for any S in S, V inner S is 0. Okay? And it turns out that this is a subspace. So let's verify. So if I have two vectors in the in S perp, then if I were to look at V plus W, I want this to be perpendicular to S as well. And if I were to take any vector in S and take the inner product, I can open this up and write it like this. But by virtue of V and W being in S perp, this is 0 and this is 0, which means that this is 0. And similarly for scalar multiplication. Let me just write it here. If I have a V in S perp and a constant C, then C times V against a vector in S, all this is the same thing as C times V against S. And this is 0, which means that this has to be 0. Okay. Now that we have this, tomorrow we're going to start with the third version of the fundamental theorem of linear algebra. So the column spaces, row spaces, left null spaces, everything, they are really related to each other in this perpendicularity relation. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today we're going to keep working on orthogonality. Here's a bunch of definitions. I'm just going to choose p many vectors in Rn, and I look at the set consisting of those p vectors. Now, a set, recall, is just an unordered list. And I'm going to call this V1 to Vp orthogonal. It's an orthogonal set if distinct vectors are perpendicular to each other. And for perpendicularity, we're using the standard definition of Vi inner product Vj equals 0. This was what we defined yesterday. Now you see, in this set, it might be the case that one of these vectors is 0, right? Because 0, the 0 vector is perpendicular to any other vector. So that's why you have this next definition. You call the set V1 to Vp orthonormal if not only are they orthogonal, but also each of these vectors have norm 1. In particular, none of them can be 0. Okay? And so here's an interesting thing, important thing. If you have an orthonormal set of vectors, then that set is also linearly independent. Okay? So here's how you can see this. So I'm assuming that V1 to Vp is orthonormal, and I want to say that these are really linearly independent. So you start with the equation for linear independence. Right, so I want to say that I have constants C1 to Cp such that 0 equals C1 V1 plus C2 V2 plus plus Cp Vp. Okay. Now, if I were to take 0 vector and take its inner product against one of these vectors, Vi, so let's say that I'm taking the inner product of 0 against V1. Certainly, that inner product will be 0. But then this 0 vector I can replace by this linear combination. Okay. And then this inner product is ultimately a matrix multiplication. So this I can split really like this. And Cp, Vp, V1. Okay? So now this is the norm squared of V1. And because we assume that this set is orthonormal, this is just 1. And any other inner product is going to be 0. Because I assume that any other, so distinct vectors are perpendicular to each other. So that means that this is 1, and this is 0, and all the others are 0. That is to say, ultimately this expression here is nothing but C1. That is to say, C1 has to be 0. Now, if I were to take any other vector here, instead of V1, if I were to take Vj, let me just write it here. So similarly, let me just write it like this. So this is equal to 0 against Vj. And then 0 is the sum over I of Civi against Vj. But then this is the sum over Ci Vi against Vj. And this is 1 only when I is equal to j, and it's 0 otherwise. So this is going to give you Cj only for any j. I just wrote down this thing in shorthand, essentially. Okay? And so for any index j, Cj has to be 0. That means that this linear combination that I started with really was using only 0 as a coefficient. So indeed, these vectors are linearly independent. Okay? So orthonormal sets are also linearly independent. And if you have sufficiently many vectors in your orthonormal set so that you span everything, or you span the subspace that you want to span, then you call it an orthonormal basis. Any questions about this? Okay. So let's move on. The next thing we want to discuss is something called the orthogonal projection. Okay. Now, it is indeed true that any subspace of Rn has a basis. We know this already. But further, any subset of Rn, any subspace of Rn has an orthonormal basis. But to come up with this orthonormal basis, it's sort of like an algorithm. And it really uses this notion of an orthogonal projection. And so for orthogonal projections, we start with two vectors. I'm taking two vectors, and I look at the span, the two-dimensional span. I'm assuming that they are not proportional. The two-dimensional span of u and v inside Rn. Okay, so the 2D and so let's say that u is somewhere here. Okay. And then v is somewhere there. Now, if I were to call this angle theta, recall that yesterday we deduced that this angle between u and v really is the arc cosine of u against v divided by u norm v norm. This was what we deduced yesterday. So today what I'd like to do is the following. I would like to take v and project it onto the line spanned by u. Okay? That is to say, I want to do basically this. Okay? I want to draw a line from v to the span of u such that this angle right here is 90 degrees. And this point I want to call, or this vector, is going to be proj sub u of v. Okay? So this is the orthogonal projection of the vector v onto the span of u. Onto u. So let's try to come up with a formula for that. So first of all, proj sub u of v is supposed to be in the span of u. Okay? That is to say, proj sub u of v is in the span of this one vector, which means that proj sub u of v is proportional to u. So there is some number that I need to figure out, such that proj sub u of v is nothing but that number times u. Okay? So I need to figure out this magnitude. This magnitude is v in norm. If that is the case, then this magnitude is v norm times cosine. So this is v norm cosine of theta. Okay? So I can take this number and put it there. This almost works. The one problem is that perhaps u itself is not unit. So its length is different than 1. So all I need to do is to essentially normalize that vector. And so that gives me this. Let me write it like this. V norm cosine of theta divided by u norm times u. Okay? So now let's recall this. So it's better perhaps to write this the other way around. So this star really tells me that u against v equals u norm v norm cosine of theta. Okay? Which means that v norm times cosine of theta, which is this expression that I see in the numerator over there, is nothing but u against v divided by u norm. Now taking this and substituting there gives me what I want. So now I'm going to see u against v divided by u norm times u norm, which is u norm squared. Okay? So that's the expression. Let me just make it clear here. Of course, u has to be a non-zero vector for this to work. And so that's the formula. The orthogonal projection of the vector v onto the span of u is given by this. U against v, that gives me a number, divided by u norm squared, that's another number, so this is a scalar. And I use that to scale the vector scale the vector u, so that gives me a vector proportional to u, so that's in the span of u. And that's the formula. Okay? Now here's an interesting thing. If I were to look at the difference between the vector v and this orthogonal projection, that vector is this vector. And based on this calculation, based on this graph or diagram, that difference is perpendicular to the span of u. Okay? So this is what I'm trying to say. V minus proj sub u of v, which is a vector on its own. It is literally this vector. It's the vector that takes this to that. If I were to take this against u, now what is this? This is v against u minus proj sub u of v against u. But this is given by that. So this is the first piece, and then this is that. U against v divided by u norm squared times u against u. Okay? So this is a constant. I can take it out. This is nothing but this. V against u minus u against v divided by u norm squared times u against u. But of course, u norm squared is exactly the same thing as this. And u against v is the same thing as v against u. So this gives you 0. That is to say, this reasoning is correct. And indeed, once you orthogonally project your vector onto u, whatever is left from your original vector, which is this, is orthogonal now. So this vector is orthogonal to u. Any questions about this? Okay, let's do examples. So here's an example. I'm looking at u equals 4, 2, and v equals 7, 6. Okay. So now let's compute the orthogonal projection of v onto the space spanned by u, which is this picture. Based on the formula, so maybe let's do it this way. We need the norm of u against v, to compute that. But also, let's also try to compute the other way around. Just like I can, just as I can project v onto u, I can project u onto v if I want it, right? So I can draw a line like this and project u orthogonally to the span of v if I want it. So let me just compute all those inner products that I'm going to need. So u against u, which is norm squared, is so 4 times 4 plus 2 times 2. So that's 16 plus 4, 20. U against v, which is the same thing as v against u. So this by this, so this is 4 times 7 plus 2 times 6. So that's 28 plus 12. That's 40. And then v against v, which is v norm squared, is 7 squared plus 6 squared. So that's 49 plus 36. And so that would give me 85. Now, we have all these numbers, so all I need to do is to put them in the correct places in the formulas, in the formula. So the orthogonal projection of V to U is U against V divided by U norm squared times U. Okay, so this number in the numerator is 40. And then the number in the denominator is 20. So 40 divided by 20, that's a number, times the vector for 2. Of course, this is nothing but 2, so I'm going to get 8, 4. Okay. So this is in the span of U. If I were to look at the rest, just as I did over here, so that I have a vector that is orthogonal to U, I would get this. So V minus proj sub U of V equals 7, 6 minus 8, 4. Now that gives me minus 1, 2. Now note that if I were to take this vector and dot product it against U, that's going to give me 0, right? Because that's minus 1 times 4 is minus 4, plus 2 times 2 is plus 4. So this is indeed perpendicular to U, and this is proportional to U. Okay? So this is perpendicular to this. So maybe I should write it like this. This is a vector in span of U perp. Okay? So this is a subspace, and I can look at the subspace as that is the orthogonal complement of this. This was something that we discussed yesterday. And likewise here, this is going to be a vector in the span of U. Any questions about this so far?
What would it mean if it was 1, negative 2, where you would still get a 0?
So 1, negative 2 is minus 1 times this. Okay. Right? So it would be not this vector, but the vector that is pointing the other way around. Okay. It would again be perpendicular to U, but it wouldn't be part of this V.
Okay.
Yeah. Any other questions? Okay. So now let's do it the other way around. Let's take U, project it onto U, onto V. And so now the U and V switches, and you need to be careful about what you're putting where. Okay. So now I need to switch the roles of U and V. So this means now in the denominator I'm going to see V norm squared, right? The numerator is again U against V. That doesn't change, but the denominator changes, V norm squared, and then I should take that constant and multiply V this time. Because proj sub V of U is the orthogonal projection of U onto V, which means that it's going to be proportional to V. So the same numbers, or similar numbers, in the numerator I'm going to have 40, in the denominator I'm going to have 85. And then my vector V is 7, 6. If I divide this by 5, I get 8. If I divide this by 5, I get 17. So this is some ugly number. So so I can write it like this. So this is 56 divided by 17, the first entry, and then 48 divided by 17, the second entry. Okay. And then let's look at the remainder. U minus proj sub v of u. Now this is going to be 4, 2 minus that vector. So let me take this 1 over 17 outside. That's a constant. So 4 times 17 is 68. 68 minus 56 is the first entry. And then 2 times 17 is 34. 34 minus 48 is some other number. And then this gives me this. 1 over 17 times, this is 12 in the first entry, and then in the second entry I have minus 14. Okay. Now let's check that indeed this vector, which is this, is perpendicular to v. Yeah, I can write this like this too. I can take a 2 out, 2 over 17, and then 6 minus 7. So this vector now becomes 2 over 17 times 6 minus 7 in the first entry. In the second entry, I want to put v, 7, 6. It's like there's a mistake somewhere. Oh no, there's no mistake. Sorry. So this is 2 over 17 times 42 minus 42. This is 0, so it's 0. So you see again, whatever was left from my vector u is indeed orthogonal or perpendicular to v. Okay. So this vector again is in the span. Now it's in the span of v, because I was projecting onto the span of v. And this other vector is in the span of v perp. Okay, maybe I should write it again. So this is in span of v. And this is in the span of v perp. Okay? Any questions about this? As you see, it's fairly straightforward, but you know, the calculations, but it can take a while to get accustomed. It's just a couple different steps involved. Okay. Let's see. So here's an interesting thing. This orthogonal projection, this idea of this orthogonal projection, is also the solution of a certain optimization problem. Okay? So this is the beginning of the so-called least squares approximations. So here's the idea. let's say u is non-zero, then the orthogonal projection of v onto the span of u so let me write it like this. Then proj sub u of v, which is in the span of u, is the unique vector in this span that minimizes the distance to v. Now, what do I mean by this? I mean this, that your task, let's say, is to minimize so let me write it like this. Cu, so the distance between v and Cu, so I'm sort of varying my vector along the span of u. Where C is arbitrary. What I wrote here really says is that this has a solution, this minimization task has a solution. C equals this number that we came up with over there, that constant that we came up with over there. The unique solution is C equals V against U divided by U norm squared. So that is to say, if I were to take any other vector proportional to U, its distance to V would be more than the distance of this to V. So here's how we can see this. I'm just going to draw the picture again. So let's look at this. So this is going to be the span of U. And somewhere here is, try to draw it better. Let's say that V is here. Somewhere here is U. And then this line is really the span of U. And what we said is that this orthogonal projection proj sub u of v is this vector. So I draw this right-angled line segment. So this vector is going to be proj sub u of v. Okay. Now, if I were to take any other vector here, let's say that I take this vector. So this is some other vector, some other candidate. At this stage, can Can you see how this should be, or why this should be the case?
What was the question?
The question is this, that I want to say that the distance of this to this is the minimum among all distances of any vector in the span of u to v. I mean, it must be the case, right? Because if unless you're not here, that means that you're going to be somewhere here, let's say, and this is a right-angled triangle, and this distance is the hypotenuse, or the square of that distance is hypotenuse, and so this has to be longer than this. Okay, that's the idea. It's that simple. So the length of this line segment is v minus proj sub u of v norm, and let's say this is the candidate v hat. The length of this is going to be v minus v hat. Then certainly this is going to be always less than or equal to this. If v hat, this candidate, is actually this point, then they're going to be the same, of course. Recall that this is nothing but the distance between v and this vector, and this is nothing but the distance between v and this v hat. Okay. So this vector minimizes the distance to v among all vectors that are proportional to u. Okay. And why is this called the least squares approximation? Because this inside this norm or the distance, there's a square root, or you're taking the squares. That's why. You can take some other power if you want it, and there's an analogous thing that you can look into. But for now, we're just looking at minimizing this distance. Okay. Any questions about this? So this idea of taking a vector and projecting onto some other vector, or the span of some other vector, is very simple in a sense, but at the same time it's very powerful. Once you understand this, and like it seems benign, but it might take a while to really get comfortable with doing calculations using this. Once you understand this, you can basically put that into an algorithm and sort of generalize it to higher dimensions. And in a sense, we've already done this. And this has to do with starting with a basis and turning it into an orthonormal basis or an orthogonal basis. So let's look at this example that we discussed earlier. So my space is two-dimensional. My vectors are two-dimensional also. And certainly, they are not proportional to each other. In other words, they are linearly independent, right? Because if I wanted, I could have computed the determinant of the 2 by 2 matrix whose columns are this by this is 24, this by this is 14. So the determinant is non-zero. So that's the basis, u and v. But u against v is not 0. That is to say, u is not perpendicular to v. So uv is a basis of the plane of R2, but it is not an orthogonal basis. So let me write it here. So this tells me that u is not perpendicular to V. What do I want to do? Maybe I should just erase this. Oh, I have a board here. So I'm continuing from there. In the previous example, this now is a basis, but it is not an orthogonal basis. Because U against V is not 0. They're not perpendicular. But still what you can do is the following. You can start with the first vector. You take your first vector, which is U in this case, because I wrote there in beta, UV. So U is my first vector. Then instead of using this guy, the second vector, what I can do is I can look at that piece. Okay? Consider instead. So I start with U, and instead of using V, I'm going to use this remainder. Okay? I'm going to take V, project it onto U over there. And then I'm going to look at this remainder vector, which I know is perpendicular to U. Okay, let's call this gamma. It's a different basis. So you see now, I started with some basis that was given to me. And then based on this, by doing this orthogonal projection and taking out this essentially redundant pieces, right? So I can think of this piece of V as the redundant piece. I really didn't need this part of V. I can just subtract it, get rid of it, and whatever is remaining is now really a perpendicular direction. So now that basis over there, this gamma basis, is an orthogonal basis. Let me write it like this. Is an orthogonal basis. And I can further modify this, okay? Because this, okay, so it's a nice vector, and this too is a nice vector, and they're perpendicular, but their norms are not 1. I also want to normalize the vectors. Well, that's straightforward. All I need to do is to essentially scale these vectors. To obtain an orthonormal basis, not only orthogonal but orthonormal, from this second basis that we came up with, all I need to do is to scale the vectors. Scale the vectors. So let me call this new basis delta. So the first vector is going to be U normalized by 1 over norm U. And then the second vector is going to be this normalized by its vector, by its norm. V minus this. Okay. So certainly this has norm 1. This too has norm 1. But let's compute these numbers or these vectors and really see that they constitute an orthonormal basis. So we computed norm squared of u, which is 20, which means that the norm is 2 root 5. So this first vector now is going to be 2 multiplied by 1 over 2 root 5. So this is going to be 2 divided by root 5, 1 divided by root 5. You see this has length 1. If you square this, you get 4 over 5. If you square this, you get 1 over 5. Add them up, you get 1. So this is a vector of length 1. So that's the first step. For the second step, we need to compute this. So now I need to compute this guy. I think we computed this somewhere. It is that vector. Of course, I forgot. Minus 1, 2. If that is the case, its norm is going to be 1 squared plus 2 squared in square root. So that's root 5. Okay? So now this vector is going to be, so let me just write the whole basis. That's my first vector. And then my second vector is going to be minus 1 divided by root 5, and then 2 divided by root 5. This has norm 1. This also has norm 1. And if you look at their inner product, it's going to give you 0. So I started with some vector, some basis beta of my space. And by just getting rid of these orthogonal projection pieces and then normalizing, I was able to obtain an orthonormal basis. Now, this procedure is called the Gram-Schmidt process. I'm running out of time, but the idea, of course, is that this is so if you were to have, n many vectors that are linearly independent, you could apply the same reasoning one by one to obtain an orthonormal basis. And so this is what is called the Gram-Schmidt process, or procedure, or algorithm. I think it's a DT process or algorithm. So you start with a subspace. You don't need to have the whole space. Subspace with a basis, any basis. So that's your input for this algorithm, and the output is going to be an orthonormal basis for the same subspace. Orthonormal for S. Okay? We're going to discuss how this algorithm actually goes. We're going to generalize it higher dimensions, but because I don't have much time today, I just wanted to leave it here. As a consequence of this, you see, any subspace has an orthonormal basis. Okay, this is very powerful, as you can see. Okay, we're going to discuss this further tomorrow. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today we're going to keep working on orthogonality. In particular, I want to discuss orthogonal projections more generally. We discussed how to orthogonally project a vector onto the span of some other vector. But in general, we would like to be able to do the same thing with spans of multiple vectors. And based on this, so underneath, there's this algorithm of the so-called Gram-Schmidt. And associated to that, there's a factorization and a language of matrices, and that is called the QR factorization. So we have lots of things to cover today, but let's start here. Orthogonal projection onto a two-dimensional subspace of Rn. Now, before we were taking two vectors and we were looking at the two-dimensional plane spanned by them, and that's what we were discussing, what we were keeping in mind when it came to angles and stuff. And now I have three vectors in Rn, and I'm assuming that they are linearly independent so that I have a three-dimensional space spanned by them. So now I'm looking at the three-dimensional slice spanned by u, v, and w in Rn. Maybe n was in the beginning 15-dimensional or 75 billion dimensional, but or dimensions. But for the purposes of this, all I need to do is to look at this specific three-dimensional section of it. And I'm calling S the plane that is spanned by u and v. And in particular, u, v is a basis for S. I'm not saying that it's an orthogonal basis or orthonormal basis. I'm just saying it's a basis. What I would like to do is to take W, the remaining vector, and project it onto the two-dimensional plane, a two-dimensional space, spanned by u and v. Okay, so I can imagine that. So imagine all the positions that you can go to using linear combinations of u and v. So maybe I should just draw it like this. Okay. There's a whole plane here, and I want proj sub s of v of w, and I want it to be orthogonal. Geometrically, what should happen is this. Okay, I should draw a line segment from W to S. So this thing that I etched is S. And I want this to be 90 degrees. Whatever vector this is, okay, this is going to be proj sub S of W. Now, to do this orthogonal projection, you really want to do it recursively. So when you're trying to orthogonally project W onto S, you don't want to start with some arbitrary vector, arbitrary basis of S. You first want to turn it into an orthonormal basis or orthogonal basis, at the very least, of S, and then go forward. So that's step one. Find an orthogonal or orthonormal basis of S. That's my first step. Now, any ideas as to how I can do this? I know that u and v constitute for me a basis for S, but, you know, this angle I don't know anything about. how can I use U and V and come up with an orthogonal or orthonormal basis for S? Any ideas? Right? Exactly. So what you can do is this. I don't know this angle between U and V, but certainly what I can do is I can project V onto U inside S. It's a two-dimensional space. I can certainly project orthogonally V onto U, and then I can look at the complement. That would be perpendicular, right? So start with U. I'm going to build a basis like this. So consider S. So now this is like this. This right here is S. It is two-dimensional. I know that it looks like this. And somewhere here is U, and somewhere there is V. This angle, I don't know what it is, but certainly I can apply this orthogonal projection business to come up with an orthogonal basis for S. So take first U. You know that U is not the zero vector. So I'm saying in my basis, my first vector is going to be U. So I fixed it, okay? So it's almost like a lockpicking, okay? So imagine that you're sort of trying to lockpick. This is sort of like the first, so when you're trying to lockpick, what it is typically is this. So you have a bunch of like cylinders here. And when you put the key in, the key has a bunch of different ups and downs. And so once you put the key into the keyhole, these ups and downs, this specific pattern for that specific lock is putting these pins in the right position, and then you get to turn this way. Okay, so this is sort of like my basis. I'm fixing the first one, and then I'm going to fix the second one, and so on. That's how it's going to go. So I fix my first vector U. I'm not going to touch that. Now I want to take an orthogonal vector, okay? Orthogonal vector, orthogonal to U in S. And for that, I'm going to use V. And how I'm going to do it is like this. I'm going to orthogonally project V onto U. This is proj sub U of V. And this vector, the vector that takes this to this, is necessarily orthogonal to U. Okay, so maybe I should put it like this. Okay, so this is the remainder, you see. This right here is V minus proj sub U of V. Yesterday we discussed how this is orthogonal to U. Okay, so this is the redundant part. It's already proportional to U. Whatever is left is going to be orthogonal to U. Okay? So now my second basis vector is going to be V minus proj sub U of V. And recall that the formula for proj sub V of U, proj sub U of V is this. U against V divided by U norm squared times U. I'm not saying anything about their norms, but certainly now the basis with u as the first vector and this as the second vector is going to be an orthogonal basis for S. So let me call it beta. Beta 1 and beta 2. Beta 1, I want to be u, and beta 2, I want to be this expression. Is an orthogonal basis. For S. Okay. Now, if I want, I could normalize beta 1 and beta 2 by scalar multiplying them by, so for instance here, 1 over beta 1 norm, and here, beta 2 I can replace by beta 2 scaled by 1 over norm of beta 2, and that would give me an orthonormal basis. But for this here, all I need is that u and v, or whatever basis that I'm looking at, for S, the angle between them is 90 degrees. So now, I'm going to change perspectives there. My picture looks like this, okay? So this is u, which is the same thing as my first vector. Somewhere here was v, okay? But instead of using v, I'm going to use beta 2, this remainder. And I know that that remainder now is orthogonal to u, okay? So this is going to be beta 2 now. And finally, we have w. Oh. So this is S. This plane is S. Okay? And somewhere here is W. And now this picture is this. Okay? This is proj sub S of W. Now, any guesses as to how I can come up with a formula for this? If this was the 1, 0, 0 vector, and this was the 1, 0, 1 vector, so that if S were the xy plane, you would just say whatever this is, so it has some height, it has a z coordinate, just zero out that 0, 0 coordinate. Right? The idea is this. If I were to look at its components relative to beta 1 and beta 2, I would be done, right? Because saying, so coming up with a formula for this vector, since this vector is supposed to be in S, and since beta is a basis for S, all I need to do is to find the coefficients. Okay, so maybe I should write that. So this is supposed to be in the subspace S, and beta is a basis for S. So really, to specify this vector, all I need to do is to say what the coefficients are if I'm using beta 1 and beta 2. So need numbers C1 and C2 such that this vector equals C1 times beta 1 plus C2 times beta 2. Okay? So, this red line segment is perpendicular to the yellow plane. Okay? Which means that so if I were to take this and move it around this way so that I see this point, so this I want to be 90 degrees and this I want to be 90 degrees as well. The point is that this is going to be the orthogonal projection of W onto beta 2. Okay? Maybe this is hard to see, but if you sort of think about it, so I can certainly take this W and project it onto beta 2, and this angle is going to be 90 degrees. And if I were to take W and project it onto beta 1, that's going to be 90 degrees as well, which means that I know the formulas for these vectors. This vector should be proj sub beta 2 of W, and this vector should be proj sub beta 1 of W. And the formulas, therefore, are the following. W against beta 1 divided by beta 1 norm squared times beta 1. And the formula for this is W against beta 2 divided by beta 2 norm squared times beta 2. Okay? Which means that you see this number should be C1 and this number should be C2. So this is C1 and this number is C2. So that the formula for the projection, orthogonal projection of W onto S, really is this. Okay? I'm going to do a numerical example in a second, but this is the formula. And of course, as you can imagine, once I have this orthogonal projection, I can again look at what is left, right? I can look at the difference between W and this projection. And that would be orthogonal to S. So if I wanted, I could keep iterating this idea to keep building orthogonal bases of larger and larger spaces. Okay, so let me write that as well, perhaps. So W minus proj sub S of W then would be a vector in S perp. Okay? Perhaps let's also verify this using these expressions. how can I verify that W minus proj sub S of W is in S perp? Well, insofar as this vector is perpendicular to any basis vector in S, I'm good. Okay? So all I need to do is to take the inner product. So that's my vector. And let's say I'm taking the inner product against beta 1. I want this to be 0. Okay? So I need to write down the expressions. So first of all, I can open this up and write it like so. And then I can replace proj sub S of W with this expression. Okay? Let me fast forward this a little bit. This is a linear combination of beta 1 and beta 2. Okay? This is a vector, this is a vector, this is a number, this is a number. And I know that I can open up additions and scalar multiplications on the inner product. So really I can write it like this. Minus. Okay? So now note that beta 1 norm squared is the same thing as beta 1 against itself. So these cancel out. This cancels out with this. And beta 2, I made sure, is orthogonal to beta 1. I don't know what this is, but certainly this is 0. And here, I have another copy of W against beta 1. And here, I'm subtracting it from it. So this is 0. OK? So whatever is left in my vector W is indeed orthogonal to S. So I did this for beta 1, but let me leave it to you to verify the same thing for beta 2. Verify the same for beta 2. Okay. I want to do an example, numerical example, as to how this works. But before that, let me ask, are there any questions? Yes.
So we started and our goal was to figure out a way to find an orthogonal projection of W onto V and or S, where S is like the subspace of V and U and V.
Mm-hmm.
How come, is it like overly reductive? Because like we started and we said we want to find like an orthogonal basis of S. And so you can kind of like conceptualize those as unit vectors, like 1, 0, and 0, 1. And so I'm just wondering to project, like I know that this is like a general formula, but how come you can't just take like the x component of, beta 1 and the y component of beta 2 and just use those for C1 and C2? Like, would that work? Or is that? Do you know what I mean?
Well, in a sense, that is essentially what we're doing. Yeah.
But this is like I realize like it's not maybe always going to be so clear.
Yeah, yeah.
Like things are going to get more abstract.
Yeah.
And that's where this formula is maybe useful.
Yeah.
But it seems like spatially that's like what we're
Yeah, exactly. Yeah. But of course, the one thing is that, let's say that you want to project, you're in 3 dimensions, and you're trying to project your vector onto the xy plane. But you forgot there's the x-axis and the y-axis. So you need to figure out an x-axis and a y-axis. Insofar as you can do that, that's good. Okay. Yeah. So let me just give a numerical example. So I want to look at vectors in R4, 4 dimensions. Okay. So here's an example. U is 1, 1, 1, 1. V is 0, 1, 1, 1. And W is 0, 0, 1, 1. And let's call S the span of UV. First, let me ask, what is the dimension of S?
Oh, the span or the...
Yeah, S is the span of these two vectors. What is the dimension? Right? Because these are linearly independent. You can immediately see this because, so if you're thinking of linear independence in terms of sort of non-redundancy, only U allows you to move in the first direction. Okay? And this doesn't allow you to do that. But of course, you can write down the linear independence equation, blah, 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 go through the motions, and you're going to see that indeed, U and V constitute a basis for S. And I want to figure out the projection, orthogonal projection, of S, of W onto S. Okay, so you see, immediately we're going to need some inner products. So that's the step 1, maybe. So that's step 2 over here. So that's step 2. These 2 boards is step 2. So I want to start with step 1. First, I need to figure out an orthogonal basis for S. And while I'm at it, I might as well turn it into an orthonormal basis, right? Because eventually I'm going to have to write down these expressions, and I see that in the denominators I'm going to see norm squares. But if before starting this I had made sure that beta 1 and beta 2 are of length 1, that is to say, this basis is an orthonormal basis, the later stages would have been much simpler to write down. So, I start with step 1. I'm going to find not an orthogonal necessarily, orthogonal, but more specifically an orthonormal basis for S. Yes. So this is all about angles. This is telling you their lengths are 1 as well. That's my first step. I need to compute a bunch of inner products. So U against U, U against V, and V against itself. What is this? So this is 1 times 1 plus 1 times 1, and so on, gives you 4. U against V, 1 times 0 plus 1 times 1 plus 1 times 1 plus 1 times 1 is 3. And in particular, I see that u and v are not perpendicular to each other, right? Their inner product is not 0. And then v against v is going to be 3. Okay? Is this clear how I'm computing this? Okay? I'm always doing the same thing. I'm taking the two vectors and I'm multiplying the corresponding entries, and then I'm adding the results, right? This by this, this by this, this by this, and so on. So my first basis vector, I want to be something proportional to u. U has length distinct than 1, so it's not of length 1, its length is 2, because the length is the square root of this. So instead of choosing beta 1 to be directly u, I'm just going to choose it to be u scaled by 1 over 2. So 1 over u norm times u, this is going to be 1 over 2 times 1, 1, 1, 1. Okay. If you wanted, you could distribute this 1 over 2, of course, but it's much more straightforward to write it like this. So I'm just going to leave it like this. So that's beta 1. That's my first basis vector. I know that at this stage it is of length 1. So that's good. Now I need to compute the orthogonal projection of v onto u. So this is u against v divided by u norm squared times u. Okay. So this is going to be 3 divided by 4, 3 over 4 times 1, 1, 1, 1. This is proportional, as you see, to u. I want the remainder. So I'm going to subtract this from v. And automatically, I know that it's going to be orthogonal or perpendicular to u, and vice versa, and likewise to beta 1. So v minus proj sub u of v is this. So 0, 1, 1, 1 minus this. 3 over 4 times 1, 1, 1, 1. Now this gives me the following. Minus 3 over 4 is the first entry, and then the other entries are 1 over 4. And perhaps it's better to write it like this. Well, let me just leave it like this. So this is orthogonal to u. But you see, it doesn't have norm 1. I need to compute its norm. So I need to take the inner product of this with itself. That gives me 9 plus 3 divided by 16. So that's 12 over 16, which is 3 over 4. This computed the norm squared. So for the norm, I need to take the square root. So that gives me root 3 over 2. And so now my second basis vector is going to be this guy normalized. Beta 2 equals 1 over v minus proj sub u of v multiplied by this vector. Of course, when you're doing these calculations, typically you don't write these down. You just go through the calculation itself, but I want to be clear as to what I'm doing, at least at this stage. So let me go over here. So this continues here. So beta 2 is going to be 2 divided by root 3 times this vector. So this vector I can write like this. 1 over 4 times minus 3, 1, 1, 1. So this is 1 over 2 root 3 times minus 3, 1, 1, 1. So this is my second basis vector. Okay? So that beta consisting of beta 1 and beta 2, where beta 1 is that, where is it? That vector. And beta 2 is this vector. Is an orthonormal basis for S. Okay. Very quickly, let's verify that they're indeed orthogonal to each other. So this by this is going to give me, you see, forget about the scalars. This by this, because I worry about the angle really. That is more important. This by this is minus 3 plus 1 plus 1 plus 1. It's going to give me 0. So they are indeed orthogonal. And if you want, you can compute the norms as well to verify that they're orthonormal. They have length 1. Okay, so this is the end of step 1.
That's just step 1.
Yes. You see, when you write abstract vectors, everything is so nice. But when you actually try to compute things, it takes a while. Okay. Any questions about the end of step 1?
Okay, so I'm going to try to cheat, and you're going to tell me why I'm wrong. Doesn't this mean that now the W, in terms of U and V, or in terms of that orthonormal basis of S, shouldn't W just be like 1/2, like the entry-wise, like shouldn't it be 1/2, 1 over 2 root 3, 1, 1?
Sorry, say again.
Like going by entries of W, for W to be projected onto S, can it be like 1/2, 1 over 2 root 3, 1, 1? Is that what we're doing, or is that wrong?
I mean, how did you come up with that? I don't understand.
Like what I was trying to say a moment ago, where it's like in three-dimensional space, like if you're trying to project a vector with a Z component onto
Yes.
the XY plane,
Yes.
you know, you just like zero out its Z component. You know what I'm saying?
I understand, but in a sense, if you're going to go, if you want to do that, like you need to change the basis for that.
Okay.
So this W is in the wrong basis, if you want, in a sense, to do that. That's why we're going through this.
I see. Okay.
Yeah. So yeah, so you can say, oh, you know, like there is some basis whose first basis element is this guy and the second basis element is this guy, so I can pretend that this is 1, 0, 0, 0, and so on. Yes, but you're changing the basis there. And this, so you could do it, but that's not, so you would need to do some calculations to translate that W to this new basis. Yeah. So this is step 3 now, step 2 now. Based on the formula, this is nothing but W against beta 1 divided by beta 1 norm squared. But you see, we already normalized this. So I don't need to write this denominator. It's going to be slightly faster. So I need to compute these inner products now. So W is 0, 0, 1, 0. Sorry, 0, 0, 1, 1. So what is this now? Times that vector. Okay. So I can take the constant out, and then this is going to be 0, 0, 2, which is 1. And then W against beta 2 is going to be 0, 0, 1, 1 against that vector, 1 over 2 root 3 times minus 3, 1, 1, 1. Again, taking the constant out, I have 0, 0, 1, 2. So that's 1 over root 3. Okay. So that means that this linear combination, so I know what this is, I know what this is, I compute it over there. Now I know this number, it is 1, and this number over here is this. So let me write it over there. Yeah. I don't remember. Okay, so writing these down now. Beta 1 is 1 over 2 times 1, 1, 1, 1. Plus 1 over root 3 times beta 2. So that's 1 over 6 times minus 3, 1, 1, 1. Adding these up, I get this. So that's 1 over 2, 1 over 2, 1 over 2, 1 over 2. And then plus minus 1 over 2. So that's minus 1 over 2, and then plus 1 over 6s. So that's 0. So this is 3 over 6, so that's 4 over 6. So 1, 1, 1, 4 over 6. Okay? So somehow this turned out to be proportional to W to begin with. Oh no, it is not proportional. It is proportional to V, sorry. So really, it turned out that when we were looking at this original picture, and we had W here, when we orthogonally project this onto this, really we hit the span of V. You see, because we ended up with a vector that is proportional to V.
So if we had picked like V as our locked vector,
Yes.
written like B1 is equal to V and then B2 is the projection, or like the complement of the projection, we would have just gotten some scalar times B1 and then nothing.
Yeah. Yeah.
So what this kind of does, it seems like, is it changes the basis for W and then
Yes.
finds the way to transition it into the new basis.
That's essentially what you're doing. Yeah. Yeah. You keep changing the basis so that your vectors look better. Yeah.
Aren't you looking for beta 3?
Say again?
Aren't you looking for beta 3?
Okay, we can do that too. But before going into that, let me just ask, are there any questions about this? So this is the orthogonal projection of this vector onto the subspace spanned by these two. Let me just check that I didn't make any mistakes. I did make a mistake. Oh no, I didn't make any mistakes. It's all good. Okay. If you want, you can do this 2 over 3, of course. So it's all good. Now I can go further, and I can say, oh, now that I have U, V, and W, I can go one step further and really say, oh, whatever is left from my W, so the difference between W and this projection is going to be perpendicular to S, which then would give me an orthogonal basis for the span of U, V, and W. Okay, I have a couple minutes, so I can do that. So this is a new example if you want. Find an orthonormal basis for the span of U, V, and W. And this is a 3-dimensional subspace in 4 dimensions. Okay, so we pretty much have everything. And I want to start with my orthonormal basis for the span of U and V. I want to add to it some orthogonal vector using W now. So what I can do is I want to have a beta 3, and that's going to be this vector right here. Right? Because this is the orthogonal projection. And this vector is going to be the difference. So I'm taking this vector. I know that it's orthogonal to S. In particular, it is orthogonal to beta 1 and beta 2. But maybe its length is not 1. So I need to normalize it. Once we compute this, then beta, or maybe I should use a different letter, or maybe not use a letter whatsoever. this now is going to be this orthonormal basis that I'm looking for.
Let's say it's an element of R4.
It's a subspace. This is what that means. So this span is a 3-dimensional space. It's in 4 dimensions. It's a subspace of 4 dimensions. I don't have time to do this calculation, but this is what you calculate. You know what this is. You know what this is, right? So you need to take this, and you need to subtract from this that vector. Then you need to scale it by its norm, or 1 over its norm, and that's going to give you beta 3. Now that beta 3 is going to be orthogonal to beta 1 and beta 2, and you know that beta 1 and beta 2 are orthogonal based on what we just computed, and you know that it has length 1. So all of these have length 1, and they are pairwise perpendicular, so that's what you want for this example. And now that I haven't done this, it becomes an exercise for you. Okay, thank you. I'll see you on Friday. Okay, let's start. Good morning. So today, finally, I'll give an explicit description of this Gram-Schmidt processor algorithm. And then we're going to sort of discuss some of the consequences of this. One of the big things, of course, is this is the third version of the fundamental theorem of linear algebra. I have a couple things I want to discuss, but we'll see. Now, let me say that on Wednesday and Tuesday and stuff, we were already doing this, except that I didn't say that we were doing this. So the Gram-Schmidt process does the following. Okay, so you start with a linear subspace S of Rn. Okay, and you also take a basis for it. And my basis is an arbitrary basis. It has p elements, which means that really I'm thinking of S to be a p-dimensional subspace of Rn. Now what I want is an orthogonal basis, gamma, and necessarily it's going to have p vectors in it because dimension is preserved. Any two bases of the same space has to have the same number of vectors that are linearly independent, either orthogonal or, if possible, orthonormal as well. And so there's this word flag. By flag, I mean the following. So if I have a basis, for instance, beta, this is an ordered tuple of vectors. So really, when I see this, I'm thinking of the span of beta 1, which is a one-dimensional space, and then a superspace of it, which is the span of beta 1 and beta 2. That's two-dimensional. And then this itself has a superspace, which is the three-dimensional space spanned by beta 1, beta 2, beta 3. So step by step, I'm sort of like getting every single dimension in S. Okay, so let me write it here. Flag of beta is the following. Increasing list of subspaces. Okay. So here you start with span of beta 1, and span of beta 1 is a subspace of span of beta 1 and beta 2, which itself is a subspace of the span of beta 1, beta 2, beta 3, and so on. And of course, ultimately you have every single vector. So you end with span of beta 1 to beta p, which is nothing but S itself. Okay, so this I'm going to call f sub 1. This is f sub 2. This is f sub 3, and S itself I can also say f sub p. And the reason why this is called a flag is that, so if you want, you can also start with the zero-dimensional subspace. So that's f1, right? It's one-dimensional. And then you turn it into 2 dimensions like this. Now you have f2. And then there's like a 3-dimensional piece, which is this and so on. It goes on like this. The point is that when I'm constructing this new orthogonal basis gamma, I want the same subspaces. Okay? Step 1, I'm choosing gamma 1, my first basis, new basis vector, to be the same thing as beta 1. Okay? I'm just looking for orthogonal. And you see the span of gamma 1 obviously is span of beta 1 because they're the same vector, and it is this one-dimensional space. Step 2, now I'm looking at gamma 2. I'm defining this to be this guy. So I'm orthogonally projecting the second basis element that I had onto the previous subspace. Whatever is left is going to be beta 2 minus this, and certainly this is going to be, by what we discussed, perpendicular to f1. And the span of gamma 1 and gamma 2 is going to be the same as the span of beta 1 and beta 2. You see, now in the first step I constructed something for this, now I'm constructing something for this. And I'm going to keep going. That's the idea. And just to make it clear, recall that the formula for this was the following. So against this, divided by gamma 1 norm squared times gamma 1. That was the formula. That's step 2. Step 3 is to keep repeating this. So gamma 3 is going to be beta 3 minus, I need to orthogonally project to the previous guy, which is going to be f2, this 2-dimensional space that I constructed in the previous step. Okay? Then again, span of gamma 1, gamma 2, gamma 3 is going to be the same as a span of beta 1, beta 2, beta 3, which is, by what we wrote over there, equal to f3. And what was the formula for this? So this has the formula that reads like so. Against gamma 1 divided by gamma 1 norm squared times gamma 1 plus beta 3 against gamma 2 divided by gamma 2 norm squared gamma 2. Certainly this is in the span of gamma 1 and gamma 2. So you keep going like this. So at step exactly P, you have the final one. Proj sub f sub p minus 1, beta sub p, and again, this is going to be something like what I wanted. And just to be explicit, the formula for this guy is this. let me use this summation notation to be slightly fast. Sum where the index goes from 1 to p minus 1, beta p against gamma I divided by gamma I norm squared times gamma I. Okay. Now, if I want an orthonormal basis, what I can do is, at any stage, instead of just staying with gamma i's, I can replace gamma I by gamma I normalized by its norm. So let me write it like this. And O and B, orthonormal basis, normalize gamma i's whenever you feel like it. Okay? Hey. So it doesn't matter at which stage you normalize these vectors, it's always going to work. But typically, if you want to end up with an orthonormal basis at the end, because at each next every next step you're going to have to normalize by this, you might as well just normalize, for instance, gamma 1 at the end of this stage before going to step 2, because if you normalize gamma 1 before going to step 2, this is going to get simplified and so on. Okay? So it's up to you. A consequence of this Gram-Schmidt process is that this is like a recursive procedure. This tells you that any subspace has an orthogonal basis, or let me say has an orthonormal basis. So that's good. Thanks. As a consequence of this, now the whole world essentially opens up. So for instance, we know that if I were to take a subspace S perp, the collection of all those vectors that are perpendicular to S, 2 is a subspace. And if I wanted, I could go further and I can take the second perp, and that would give me the original guy. So S double perp equals S. Okay? Another thing, for any subspace, the dimension of S and the dimension of S perp would add up to n. Okay? Which means that if you have, let's say, a 3-dimensional subspace and a 15-dimensional ambient space, its perpendicular would have 12 dimensions.
I'm sorry, do you mind repeating that?
Maybe numbers were wrong. If you have a 5-dimensional space inside a 15-dimensional space, its perpendicular will be 10-dimensional.
Oh, so it's just going to be like the dimension of the encompassing space.
Yes. Yeah. Ambient. Yeah, that's what I meant. Yeah. Okay, so now that we have this, now I can state the final version of the fundamental theorem of linear algebra, at least for the purposes of this class. This is such an important idea that, you can make a living as a mathematician by proving generalizations of it, even to this day. Huh?
My takeaway is that this will be on midterm 3.
Yeah, probably, yeah. So the fundamental theorem of linear algebra, Mark III. So we start with an m by n matrix. And recall that I can think of this as a linear transformation from Rn to Rm. Does any of you remember anything about this? We had a bunch of things, items, in this fundamental theorem of linear algebra. So it should say something about ranks and nullities, right?
Oh, the rank and the nullity adds up to the dimension of.
Yeah, so let me record it here. So if I have this thing, so I have 4 subspaces. These are the 4 important subspaces that you get to attach to A. Column space of A, null space of A, column space of A transpose, null space of A transpose, right? So column space of A, null space of A, and then null space of A transpose, and then the column space of A transpose. Now these first two, column space of A and the null space of A transpose, are going to be subspaces in Rm. And these two, the null space of A and the column space of A transpose, because A transpose goes the other way around, right, are subspaces of Rn. Recall that the dimension of the column space of whatever was called the rank, and the dimension of the null space was called the nullity. And we started, let's say 2 months ago or something, with some numerics about these numbers, so some relations about these numbers. So 1, rank of A plus nullity of A equals n. Applying the same thing to A transpose, I have this. Third, these two numbers were the same. So the rank of A is the same thing as the rank of A transpose. Okay, these we had already. So now let's talk about perpendicularity. The two subspaces in Rm are perpendicular, and the two subspaces here in Rn are perpendicular. This is the addition. So the column space of A, perp, is the null space of A transpose. Null space of A, perp, is the column space of A transpose. Okay? You see, this subspace and this subspace are both in Rm. So it makes sense to take the perpendicular of this. And it is believable, possibly, that when you take the perp of the column space of A, you get this other one. And of course, if I wanted, I could also write it like this. Null space of A transpose perp equals column space. So and null space of A equals column space of A transpose perp, using essentially this idea over here. What else? Okay. Next. Since the rank of A is the same thing as the rank of A transpose, and since rank is the same thing as the dimension of the column space, I have that the column space of A has the same dimension as the column space of A transpose. Now we discussed how dimension, this number, is the only invariant for isomorphism. That is to say, if two subspaces or if two vector spaces have the same dimension, same finite dimension, they are isomorphic. Okay? This we have already from item 3. But further, what you can say is that if you restrict your matrix A to the column space of A transpose, that's going to be an isomorphism. So 5, 6. So for that, I'm going to denote it like this. A restricted to column space of A transpose is an isomorphism of vector spaces between the column space of A transpose and column space of A. And I can do the same thing with A transpose, of course. A transpose restricted to the column space of A is going to be an isomorphism from the column space of A to the column space of A transpose. Now, thinking of this in terms of matrix factorizations, you can say that there are two invertible matrices. So A equals L. So let me say star R for some invertible L and R such that this star, this top right, top left corner, corresponds to this restriction, and it's an isomorphism. Okay. Are there any other? No, this is all I wanted to say. So 8 items, okay? These are all essentially the same thing. What is, of course, important is 1, 3, and 4. If you can keep in mind 1, 3, and 4, you can come up with the other ones by permuting the symbols.
Number 4 says that the column space, the column space of A, or everything that's perpendicular to the column space of A, is the null space of A transpose.
Yes.
And I guess like the way that I'm thinking about that is that the column space of A is basically the span of A, right?
Span of the columns of A.
The span of the columns of A.
Yes.
And so basically that's saying like everything that's not in the span of A is perpendicular to A, and everything that's not in the span of all those columns of A is the null space.
It's not quite what you're saying, because, so think of it like this. So consider this subspace, the x coordinate. And I can take a vector that is not in this, for instance this. This vector is not certain in this, but it's also not perpendicular.
Okay.
So I'm saying that if you were to draw, for instance, the column space of A and the null space of A transpose, they're going to be perpendicular things.
Okay, so So it's not everything outside the column space of A. It's just
Yeah.
specifically what's perpendicular is also null.
Yes, yes. So the picture you should keep in mind is something like this, okay? So let's say that this is a caricature, of course. This is going to be Rn, and this is going to be Rm. Let's say that this right here, the x-axis, really is a caricature for the column space of A. So any vector that you start with, if you apply A, ends up in the red line, okay? And of course, I can go backwards. Maybe I should use red for A. And let's use blue for A transpose. I'm not saying that A transpose is the inverse of A or anything like that. The relationship is slightly more complicated. But just as I can look at the column space of A, I can look at the column space of A transpose. That's going to be, I take any vector from here, I use A transpose, and that's always going to give me a vector here. Now, this is going to be the null space of A. Okay? What is the dimension? Well, its dimension is n minus the rank of A, whatever that number is. Okay? I don't know that number, but I know that if I apply A to any vector in the null space, which is the green line, I'm going to end up here. And likewise, this thing is the null space of A transpose. And again, I don't know the dimension of it. Again, all I know is that the dimension of this is going to be m minus the rank of A. And I know that whenever I apply A transpose to any vector in this yellow line, I'm going to end up at the origin. Okay? So this is some intricate dance happening. And this is 90 degrees, and this is 90 degrees. Okay? That's the picture. This takes a while to digest. But it's very powerful. It's very useful. Okay, so let me give the statement of something that is also very popular. It's called the Fredholm alternative. This actually, I think, first was discovered by Fredholm in the context of solving linear differential equations. Linear differential equations, solving them is basically solving linear systems but in infinite dimensions. So your vector space is the function space or some function space, and you're trying to find a solution. And the Fredholm alternative says the following. Given a matrix and a vector, so let's say that I have an m by n matrix and a vector b that is m-dimensional, and I'm interested in solving ax equals b, right? This is what we started with. The Fredholm alternative says the following. Then ax equals b, this linear system is consistent. That is to say, it has a solution x. So now the alternative. XOR A transpose y equals 0 and y perpendicular to b is consistent. That is to say, if you have this system, okay, you have your matrix and you have your right-hand side, your output vector. Certainly, you can look at A transpose and set the right-hand side equal to 0. What this is saying is that both of these systems cannot be consistent simultaneously. If you can find an x that solves this, there is no y that solves that, and vice versa. Okay? Exclusive or. So either this or this, and if this, not that, if this, not this. Exclusive. So this means exclusive or. Exactly one of these two situations happen. One of these two boxes hold. Okay?
Something that comes up when we think about solving linear systems of partial.
No, this is just matrices. This is just linear systems.
Well, so yeah, I guess what it's like literally saying is like if you're interested in solving Ax equals B, another approach is looking at its transpose and asking the question.
Yes.
Is there a way to solve it for some y where y is perpendicular to your vector?
Yeah. Yeah.
Okay.
Yeah. And so how can I argue that this is indeed the case? Well, let's just assume the fundamental theorem of linear algebra. If you have time, maybe I'll discuss at least this fourth item. We had discussed these first three already. Maybe I can discuss the fourth and fifth item. And the other ones are sort of like, upscale statements of the same idea. But given the fundamental theorem of linear algebra, why should this be true? Why is this alternative the case? Well, this left box is the same thing as, let me say it like this. Left box holds if and only if B is in the column space of A, right? Because if you can solve this for X, that means that B is in the column space. So this box is the same thing as saying that B is in the column space of A. And that box, at least A transpose Y equals 0, means Y is in the null space of A transpose, and Y is perpendicular to B. Okay. Well, we know that the column space of A is nothing but the null space of A. Not perpendicular. I should have said not perpendicular, I think. We'll see. So column space of A is the same thing as the null space of A transpose perpendicular. So this is the same thing as null A transpose perp okay, yeah. So let me write it like this. Not perpendicular. then it is correct. But if this is the case, then B is perpendicular to any vector in the null space of A transpose, and Y is in this space. So okay, so because of this, this and this cannot hold at the same time. So this is sort of how we can think of this Fredholm alternative. It's really sort of like a restatement of this, but it's a popular restatement, so I wanted to mention it. Do you have a question? Yeah.
So if you're interested in, if, like say you're working in like an m-dimensional space, and you have one vector that lives in one subspace and one vector that lives in another subspace. If you've already shown that your first vector is orthogonal to the subspace that the second vector lives in, because that second vector it's like confined to that subspace, and you've already shown the first vector is orthogonal to that subspace, you don't have to check that those two vectors are orthogonal. You already know they're orthogonal. Like
probably. I mean, probably in order for me to say something more specific, you would need to write it down. But probably what you're saying is correct.
like I guess like if you like to make it a real example. Like
yes.
If you had a vector in R2.
Yes.
And then you had a vector in R3 that is orthogonal to R2. And then you had an arbitrary vector in R2. You already know that your vector in R2.
Yes, that is true.
Okay.
That is true. Yeah, that is true. Okay. Okay. Now, we have two more items. One of them is the so-called QR factorization. And the other one is, I wanted to mention this least squares approximation again. You mentioned this in the context of projecting onto one-dimensional subspaces. But of course, the idea holds for general subspaces. Let's start with least squares approximation. Again, I start with an m by n matrix. And let's say that I have a vector in Rm, and I want to solve Ax equals b for x. So this is what I want to do. And we have discussed many methods of solving this row reduction, whatever. And we have this dichotomy, right? Either B is in the column space, in which case you can actually solve this, or it's not, in which case there's no solution. So either the system is consistent or it is inconsistent. Now, if the system is not consistent, you can say, okay, this doesn't have any solutions. And you can say this is like the end of the story. Or you can say, what is the best solution I can find? Best approximate solution. So instead of doing this, okay, if this is not feasible, you ask for something less. And ask, instead of saying, I want an x that exactly hits b when I apply a to it, you say, I want to minimize the distance between these two. So find an x. If you can find an x such that this distance is 0, you actually solve the equation, of course, because the only vector whose norm is 0 is the 0 vector. Or in other words, if two vectors have, if the distance between two vectors is 0, that means that those two vectors have to be the same. So this is this idea of giving yourself an epsilon of room, essentially. Let me not write it. So underneath is this idea, like how do you find this, is an orthogonal projection, of course. Because orthogonal projections tell you the closest vector in a certain subspace relative to some other fixed vector. So this is the picture. I have Rm, and I apply A to it, and now I'm in Rn. And let's say that this is the column space. Geometrically, this system being inconsistent corresponds to the following. My output vector, the vector that I want to get, is somewhere here. It's not in the column space. So this is the geometric representation of ax equals b being inconsistent. Okay. Now let me look at this. This is a subspace. I can orthogonally project this vector onto this. And now I have a candidate here. Let me call that b hat, following the notation in the book. So this is proj sub column space of A of B. Now I know now that AX equals B hat is a consistent system, right? Because it's in the B hat is in the column space. So let me say AX hat equals B hat is consistent. Further, the distance between B and B hat is going to be sort of like an error. And if I were to look at that difference, so B minus B hat is this vector. Now that vector is, so what was this space? The space that is orthogonal to column space of A. Based on the fundamental theorem.
The nullity of A transpose.
Null space of A transpose. So this is in the null space of A transpose, which by the fundamental theorem is the same thing. Oh, that's all I wanted, sorry. This is all I wanted. So maybe I should write it like this. B minus B hat is in the column space of A perp, which we know to be the null space of A transpose, which means that A transpose times this is 0, which means that A transpose times T times B equals A transpose times B hat. And B hat is supposed to be A times X hat. Okay? So now we have this new equation. This is a consistent equation because there's some X hat that solves this. And the solution to this is giving you the best approximation. Okay? So this is called the normal equation. Okay. If you can, so this x hat is going to be the x that minimizes this distance. Okay. Let me not write it. Oh, I have time, I think. I have time. I'm writing it. Okay. This system what was it? A transpose A. X hat equals A transpose B, which I obtained by just starting with AX equals B, and I applied A transpose to both of them, both sides. This is consistent. Any X hat that solves it minimizes that distance, AX minus B in norm. So you see, X hat would be the best approximation to a solution to AX equals B. Why is it called least squares? Because inside this norm, there are squares, right? You take the square of each entry, and then you add them up, and then you take the square root. There are other norms. There are other norms that you can use. There are other metrics that you can use. But this is one of the most popular ones. So that's why we just mentioned this. So one final thing is this QR factorization. Let me just mention this super fast. On Monday, I'm going to take some time to go more into detail with this QR factorization. And also, I want to give this abstract definition of an inner product space. But here's the idea. This is the underlying idea. If I were to start with a subspace with an orthonormal basis, this is in Rn, and let's say that gamma is an orthonormal basis for S. Now we know that the proj sub S of V for some vector, the orthogonal projection, has the following expression. So V against gamma I multiplied by gamma I. This is a number. This is a vector. This is a linear combination of these vectors, gamma 1 to gamma p. Now I can write this like this. I take all these vectors and consider them to be the columns of a certain matrix. Okay? That's an m by p matrix. And now this would be the same thing as this. Let me call this B or C. Then I can realize that this really is C transpose applied to the vector V. Okay? That is to say, this orthogonal projection is given by C times C transpose. This is the first stage of the QR factorization. You sort of like store orthogonal projections into a matrix, and then you split whatever matrix that you start with using these sorts of matrices. Okay? We're going to discuss this on Monday. This QR factorization is a factorization that just comes out of this Gram-Schmidt algorithm. Just like in the row reduction algorithm, when you sort of like thought of it in terms of matrix multiplication, that gave you LU factorization. This time it gives you some other factorization. That is also very useful in many tasks that involve solving things, finding eigenvalues and everything. Okay? But this is most of what I wanted to cover regarding orthogonality. Hopefully by the end of today you'll get your next problem set. I'm having trouble sort of finding nice problems. I mean, I'm not having trouble finding nice problems, but appropriately nice problems, let's say. I'm finding inappropriate problems. So, okay, thank you. Have a nice weekend. I'll see you on Monday.